Greetings, everybody. We're going to do some mechanisms for our final, some biological aldol condensations and Claisen condensations. This is acetyl-CoA here. You don't need to write that down. And so I guess for the activity portion, copy this. And the mechanism we're going to do, just this one. We'll do the whole thing here, but for your activity, can you copy all that? And I'll slowly get started on the mechanism. I'll talk about the mechanism so you can listen on the video after you get home. When we make a product that's a alpha, a beta, keto, ester, you should be thinking Claisen condensation. But I have good news. On the final exam, you don't even have to be thinking Claisen condensation because the Claisen condensation will be written right there. And remember, on the final, you're choosing between two mechanisms, just like in Organic Chemistry 1. You're always choosing between two mechanisms. So this could be one, and it could be a different mechanism underneath. And it would have the words on the top. And the next one's going to be an aldol condensation. Trying to make it look like the final. Don't copy that. And this would be NADH reduction. So to do a Claisen condensation, you're going to need an alpha H and a base. When you have a biochemical reaction, the base will be the enzyme with a lone pair, and the conjugate acid, when you need it, will be this. As per usual, we're going to go red first, baby blue second, and purple third. And we got the enzyme coming in, grabbing an H, making an enolate. Enolate is named after the resonance form of this species. It's going to attack the second molecule of acetyl-CoA. Well, I got to fit inside the yellow box now. That is a challenge for me. Okay, let's work this. I think if we come around here, yeah, hits the carbonyl. Pi becomes lone pair. Lone pair comes back. We've done this hundreds of times, right? Kick off our leaving group, which happens to have a lone pair on sulfur already. In green here, which can protonate from the conjugate acid of the enzyme. And that's your HS-CoA happening right there. And here, I think we made our product. I think that's it. I got to caution you, this is different than the Claisen condensation we did in lecture, because in lecture, the leaving group here is also a strong base. It was an alkoxide with an O. This leaving group's not a strong base, so it won't take the alpha H between these two carbonyls. Remember, this is a very special alpha H that has a pKa of 10. And that's why we took it off in our normal Claisen, and then we had to put it back on in step 2, where we added HCl. Biochemistry, you don't need that stuff. So biochemistry can sometimes save us things. All right, so that right there is your activity. And the rest I just want you to watch. We're going to start off by taking the H off this again. Bless you. Take the H off again. And we got to watch what happens carefully. Okay, I'm going to take that off. Make this species here. Again. And realize that that part is this part. And it attacked a carbon that had a methyl on it. And the carbon with the methyl on it became an alcohol. So this is the only carbon with a methyl on it. And it can become an alcohol after it gets attacked. Oh, yeah, I know you want to take that H off because the pKa is lower, but it doesn't get you to this product no matter what you do. Not productive. And in biochemistry, because things are all about enzymes, we can take an H with a higher pKa before an H with a lower pKa, because when that substrate, it's just a way of saying a reactant, when a substrate fits in the enzyme's active site, the base will grab the proton that's nearest to it. So if that pKa 10 is nowhere near the base, then it won't be taken. And yeah, this thing fits in the active site, and the H gets grabbed, and it's an attacker of the carbonyl that's the beta over there. Here it comes. I know it's going inside the box. You don't have to copy this on your activity. Same story. And then you're going to protonate after you get an O minus. H enzyme looks like a candidate, doesn't it? It gives us the product, by the way. Without crossing arrows, that's going to be tricky, but I think I can do it. There's my H enzyme. There you go. Now, ladies and gentlemen, I know we didn't talk a lot about NADH and NAD, but the fact is there's two H's here. And in the end, there's only one H. This is your hydride. One of those H's is hydride. It will be kicked off with this lone pair and delivered to something that's positive. Lone pair, nitrogen resonates it in. Resonate, resonate. Well, attack. There's hydride taking its electrons and attacking a carbonyl. Just like AlH4 negative when you made H minus from it. There it is, H minus doing its thing. Dump a pair on there. We could kick it off and be done. Baby blue. I believe on most of your tests, I realize this is not really worth 5 points. I suppose I didn't even grade this part where S-CoA, I don't think I put it on the key that S-CoA picks up a proton, but I see it does have a proton at the end. So very similar to S-CoA leaving last time. That gets us there. And there. Pretty sure. Yeah. And then you'll see that reduced all the way to an alcohol in biochemistry. And then that becomes mevalonate. Mevalonate is the precursor to all those terpenes. Good stuff. Cholesterol comes from terpenes. Did you know that? Mm-hmm. All of the steroids with the ABCD ring systems, they come from terpenes. That's terpene chemistry that makes those. All right, so that's activity 3, I guess, today. Just in the box. And then we'll do another activity after we come back. trying to end here.